Part B of our regression and correlation presentation talks about correlation and tests for linearity. An extremely important statistic that goes along with regression is called the coefficient of correlation, or the correlation. And it's designated by the lowercase letter r. And you'll see that in almost every statistics textbook that talks about correlation. It'll talk about r, the coefficient of correlation. R has a range from -1 to +1, and it's a measure of the relationship, the strength of the linear relationship between x and y. If x and y have a positive slope, then r is greater than 0. If x and y have a linear negative slope, then r is less than 1. And the larger that the r value is, either closer to -1 or closer to +1, the closer or stronger the relationship is between x and y, and the closer the data will fall to a straight line. For example, a value of r equals 0.85 is a strong positive relationship. An r value that gets close to 0 indicates that there's no relationship between x and y, or that it's extremely weak. Another very important and widely used statistic is the coefficient of determination, or r squared, and it literally is r squared. Whatever value you get of r, if you square it, you will get r squared. R squared has a range from 0 to 1, because the negative values of r, when you square a negative number, you get a positive number. So r squared always has a positive number. R squared with a capital usually refers to multiple regression, which will be covered in another part. But it also shows the strength of relationship between x and y, but it kind of is more of an indication of what proportion of the variation is explained by the relationship between x and y. For example, with the stock example we used in the last part, it turns out that r squared is equal to 0.72. Our interpretation is that 72% of the variation in stock ownership can be explained by the independent variable x. And this is helpful to know. On this slide we have the equation for calculating r, the correlation coefficient. This is sometimes known as Pearson's r. You'll see that it asks for a variety of different statistics. Most of these were on the spreadsheet that was created in Part 1, or Part A, for calculating B0 and B1. There was one of these statistics on this equation that wasn't on that spreadsheet, and that's explained on the next slide. What you need in addition to what you've already calculated is the sum of the y-squareds. So you need to add another column to the spreadsheet, square all the values of y, and then add them up. Then you'll have the sum of the y-squareds. There's an alternative version of this same formula in many textbooks. One example would be in Hayter's textbook, Probability and Statistics for Engineers, 3rd edition, on page 585. Let's take a few minutes and look at what different values of r mean. If we look at these plots of x versus y, and plots of paired data like this are sometimes called scattergrams. If we look at these scattergrams with different patterns, what would the corresponding value of r be? In the first one, situation 1, we have a straight line, and that's where we have a very strong correlation between x and y. An extreme situation, in fact, is the straight line. And when we have these extreme situations, then r is either +1 or -1. Since this is a negative slope, this is an r value of -1. Situation 2, we have a fairly strong relationship between x and y. and it's a positive relationship, a positive slope. So this is going to have a high R value. It's not going to be 1 because it's not a straight line. The next slide shows that there isn't much correlation between x and y because knowing the value of x doesn't really seem to help you predict the value of y. In fact, the relationship is a flat line or a linear straight line that just is horizontal. And in this case, we say there's no relationship and the correlation coefficient is 0. Now situation 4 has the same pattern as situation 3. And that's just to illustrate that it doesn't matter where in the quadrant we have this pattern. The fact that there's basically a flat line showing the relationship between the two shows that R is equal to or close to being equal to 0. Situation 5, we have a straight line again. So we have a correlation of +1 in this case, since the slope is positive. And finally, situation 6, we have a strong correlation, but it's negative in this case. So this will be a large value of R that's negative. So to wrap up the previous slide, we see that what the R values are, and some of them were already mentioned, but you'll notice that situation 2 and situation 5 represented strong relationships, one being around a plus 0.9 and the other being around a minus 0.9. Now we're going to talk for a minute about hypothesis tests to test for linearity to see if there is a significant relationship between x and y. We need to point out that if x and y are not related, in other words, if knowing x doesn't help us predict y, then we have a line that's usually flat, and the best estimate of y is just the average of y. Knowing x isn't helpful. If the value of y does change with x, then using the regression line to predict y is preferred. And so we want to test to see if this relationship really is significant. There are actually several different hypothesis tests that we can use to test for linearity. One is to test whether or not R, and the parameter for R is rho, the Greek letter, but the hypothesis would be to test whether or not R is 0 or whether or not it's not 0. And we use a t-test for that, and the t-statistic is shown. And so if we plug in the value of R and then compare that t-statistic to the appropriate critical value, we can determine if it's a significant relationship or not. Likewise, another way to test for this is to see if the slope is 0 or if it's greater than 0. And we have a t-statistic for that. It's shown here. And B1, the slope, divided by the standard deviation of y around the regression line, divided by, and then there's some statistics there that we've already calculated. Here we get another test statistic, and we can compare to the appropriate critical value to test for whether or not there's a significant relationship. Note that if the line doesn't have a slope, if the slope is 0, it's a flat line. The third test we can conduct is called the global Ftest, and this will also tell us if there's no linear relationship between x and y, because what it's doing is it's seeing if the sum of the squares due to regression are close to being equal to the sum of squared errors. In other words, are we just looking at random error, or are we looking at a significant relationship? This is more widely used for multiple regression, and note that the F-test here for the simple linear regression should give you the same result as the t-test on beta 1. Here we have the statistics from a software package that was used to complete the regression analysis. You'll see the top line shows that the R value of 0.849, and this is for the stock data used in Part A. If you square that, you get R squared is 0.72. So there's a fairly strong correlation between X and Y in this data set. If you go down to the regression, or rather the ANOVA table, it shows on the far right, it shows F and the significance of F. The F is calculated by computing sums of squares and then a ratio of the mean square error to the residual square error. And the p-value or significance of F is 0.008. So if we were testing the hypothesis that there was no linearity, we would reject that null hypothesis because we have a p-value of 0.008. If we had been using a significance level of 0.01 or something like that, we would have clearly rejected the null hypothesis. And likewise, if we look at the t-value calculated from one of those other tests, we got a p-value of 0.008 as well. So we see here that we would reject the null hypothesis, that there is no linearity, and in favor of the alternative, which says there is some kind of a linear relationship between X and Y.